So the second of our speakers on our Smart City session is Professor Carlo Ratti, who is director of the MIT Senseable City Lab. Please come on up, Carlo.
Thank you. Hello. Good morning, everybody. Great pleasure to be back here in Dubai with all of you. So I wanted to start with some images that a bunch of artists did about the future of mobility over 100 years ago. It was the end of the 19th century, and they imagined how the future would have been. And so they got some things right. They saw mechanization in agriculture coming, as you see here. They even predicted Roomba, or something like Roomba, in our homes. But they also got many, many things wrong. They thought that actually the police would actually be moving like this. Not even in Dubai, this has happened yet. That we would move in the oceans like this, or that firemen would actually behave like this. And the reason I'm showing you this is that yesterday, we've been talking a lot about future. But the future is something that's impossible to predict. That point was famously made by many people, including the great philosopher Karl Popper. The future depends on things that have still to be developed in terms of thinking. Maybe some of you getting out of the conference today will get some incredible idea that might change the future. We don't know that yet. So we cannot predict it. We all contribute to determining it by what we do. As Popper says, we're all equally responsible for its success. So what we can do then is work on the present and trying to transform it. And that's what we're passionate about. We do it at MIT Senseable City Lab in Boston, with the lab also in Singapore. We're doing with our design office and some of the startups that are coming out of both of them. Over the past 5 years, we've grown the startup ecosystem. We raised around $50 million of venture capital funds, and we got a few hundred people now working in that part. So let me show you the type of things that we do. And I show mostly the research here, not much about our design office. So today we can see a city like this. We couldn't a few years ago, a city like a living organism. Then if you take data such as this one, you can do interesting things. That's exactly the same data in New York. Every dot is a taxi pickup or drop-off. The yellow dot is a pickup, the blue dot is a drop-off. Which place is this, by the way? Yes, JFK Airport. So if you zoom out, you see JFK down there, you see Manhattan and all of the boroughs. And for instance, we started analyzing all of this data. You can say big data in city. And the first question we asked was, well, if you look at those 2 points in Manhattan, you got hundreds of thousands of trips connecting them in the course of the year. So how many trips could be shared? Now, if you want to answer that question mathematically, you need quite sophisticated mathematics. Traditional tools fail when you got such big data. Sometimes we say big data also requires big math or new math. So we developed an approach based on network science. You see here this kind of shareability networks we developed. And what we discovered actually is that in New York, you could take everybody to destination exactly when they need to be there, give or take 1, 2, or 3 minutes, but with 40% less vehicles than what we have today. Incidentally, when the results came out a few years ago, they started a nice debate. They also came to the attention of Uber. At the time, Uber had not launched Uber Pool yet. And then we started a collaboration between MIT and Uber. And as you might know now, Uber Pool does exactly this. Allows 2 people going more or less in the same direction to share a ride, which means one less car on the road, which is less congestion, less energy consumption, and ultimately, a better environment in our cities. Now, more recently, just last year, we did another piece of research on the same data set. It was published in Nature. And here we actually ask ourselves another question. When you think about the future, then cars, especially autonomous cars or cars in general, are going to be quite a commodity when you think about mobility systems, when you think about mobility on demand. So the important thing is how you do dispatching. So we looked at possible optimization of dispatching in New York. We called it the minimum fleet problem. So what is the minimum fleet to keep New York on the move with all the trips it requires? No sharing at all. Here's a short video. So basically, the idea that tomorrow we can actually run a big city such as New York with half of the fleet we have today. And actually, the interesting thing is that this is the latest startup that came out of the lab. And I believe they already started a partnership with Dubai in order to look at optimizing the dispatching of taxis in Dubai. And tomorrow, the same thing is about optimizing the dispatching of bigger fleets as we move to autonomous cars. And if you're interested on the website, you can find all the data, you can play with it. We think that sharing data is also very important. It allows all of us to really put our hands in the data and better understand the cities we live in. Now, another thing I want to mention, so this was about doing some research, taking data from movements. So every vehicle is a GPS point moving over time, and then we use that in order to understand movement in the city and how it can be improved. But the car itself is collecting more and more data, not only GPS traces, but thousands of points. And what you see here is actually the average number of sensors you got on a car today is 2,000 to 3,000, which are mapped over there. So recently we started using the car as a way to sense the city. The car is an ambient sensing platform. By the way, I'm showing some papers here. I've shown them before as well. All of them are available on our website. If you're interested in the maths, just you can download them. They're all free access on the MIT site. So we started looking at this, and for instance, we look at a big problem, which is monitoring infrastructure. If you look at this, it's actually a famous crash of a bridge. That's a Tacoma bridge that collapsed because it started resonating. But there's another example which is closer to us. That's Longfellow Bridge. To the left, you got the beginning of the MIT campus. And Longfellow Bridge, a few years ago, was monitored. It had not been monitored for quite a number of years. They discovered it has very serious structural flaws, and so they decided to basically stop it, close it. Two sides of the city were totally cut, had no connection for a number of years. It was rebuilt at a very huge cost of a few $100 million. And the reason for that is that it had not been monitored in a regular way. So at one point when analyses were made, they realized that actually its status was so critical that it had to be basically rebuilt. And the reason for that is that monitoring a bridge today is very expensive. If you look at this, is how we monitor bridges such as the Golden Gate. We put sensors, like you see to the left, or we send people to inspect the bridge. But in both cases, the cost can be huge. For sensors and for cabling the sensors and collecting data and analyzing the data, you're talking about something that could be $500,000 US per year. So our idea was, well, in order to get this data, which is what you get from the sensors on the bridge, is vibration data, why don't we use all the sensors we now have in cars and in our pockets? So if you look at accelerometers, every car today has an accelerometer, but also every phone today, like this phone, any smartphone you have, has accelerometers. So we decided, what about using this in order to monitor the infrastructure? So we used the data from the car, from those 3 phones, and also from the little box, the orange box, which is a professional accelerometer. And then we started going back and forth across the bridge. We picked the Golden Gate because we know everything about it. So the ground truth for that bridge is very, very good. So we started going back and forth across the bridge over 100 times. That's why you want to have a lot of graduate students involved in research. After 100 times, actually, the San Francisco police got a little bit suspicious, so they stopped us. But we collected all the data, which you see here. So that's the data, the raw data we collected on the bridge. And by analyzing, actually, we realized that we can actually detect the main frequencies of the bridge, which in turn can be linked to its structural safety. So some structural health. So somehow now we are scaling this up with data from Uber and data from a big insurance company to look at the whole country and do this almost like an early warning system, a system that can scan thousands of bridges across the country, can look at places where actually you got changes happening in the vibration modes of a piece of infrastructure, and then at the point, you can decide when you want to go and install additional sensors. So it becomes a little bit like when you go to hospital. The first thing they do, they actually will measure your blood pressure, your temperature, but then if you see something is wrong, you can do additional, you can be sent for an MRI, an X-ray, additional analysis. So in a similar way, we want to use this, we're starting to use this at the scale of an entire country in the US and in a European country in order to monitor all of the road infrastructure. Again, ubiquitous sensors allow us to better understand what's going on in cities and on the road. Now, I was saying that the car has around 2,000 to 3,000 sensors. If you add 2 additional ones, like 2 little ears there, then the car does a 3-dimensional scan of the city. Those are called LiDAR. You feed all of this in an artificial intelligence system, and the car drives itself. And that's not the distant future or the future, that's the present. We've been involved with the government of Singapore, helping the government of Singapore since 2014 with their self-driving car system. It's probably one of the most advanced cities in the world today, Singapore, in terms of testing autonomous cars. And you know, as we speak, there's hundreds of them being tested on the road and also being used by people. Now, the interesting thing when you got this is that you radically change the way we move in the city. And the reason is that today, a car is parked on average 95% of the time. We use it 5% of the time in the United States, 95% of the time. It is somewhere, not only it's not used, but it uses valuable space in our cities. And that's why we got, you know, parking, humongous parking lots, like you see here. Now, if you actually move to a self-driving system, that can change, because the car doesn't need to be parked. It can give you a lift, and then can give a lift to somebody else in your family, or to anybody else in the city. So it can be always on the system. And so as a result of that, there's some work we are just publishing right now in Singapore. Singapore has 1,370,000 parking spots. And if you were to move to an autonomous system, you know, that could be cut by over 70%. Now, some of this is published. We're doing some additional papers. But basically, potentially, we could free a lot of space in our cities. And that's going to be very, very interesting. The other thing, when you look at a few years down the road, then other things might change. For instance, this. You know, that's a very well-known traffic light. And traffic lights appear on our roads when cars appear on our roads. But you've got an intelligent system where every car knows where it is, and where all the other cars are. You don't need to stop anymore at the traffic light. You can keep on going, just avoiding collisions, like this. Don't try it yet? I showed this in Naples, and they told me, so what is new here? Now, I'm Italian, so I can make such politically incorrect jokes, but I got corroborating evidence from a former Italian minister who said that in Milan, traffic lights are instructions. In Rome, there are suggestions. In Naples, they are Christmas decorations. So again, we're doing a lot of mathematics to study this. There's actually a patent by MIT. You know, a lot of this is the work we do at the lab, and a lot of this is then what MIT sometimes will protect and license, or it will be used for startups. But if you look at this paper uses an extension to queuing theory in order to address that problem of the intersection and find new solutions to it based on what I just showed you. Now, I want to start wrapping up telling you about other type of movements. For instance, we got now a very, very exciting collaboration with the city of Amsterdam, and in particular with an institution called AMS, Amsterdam Metropolitan Solutions. And so we started looking at mobility in Amsterdam. And mobility means a lot of water mobility. There's a lot of canals. And so you move parcels like this, you move people like this. So we started thinking, what about developing self-driving boats? We call them robots. So what can you do with a robot? You could use it for what I said before. You can use it to move parcels, people. You can use it to sense the water quality, the air quality. But also you could use them like a floating responsive platform that basically self-assembles when you need it. Think about an architecture in the city that can constantly change. You need a temporary bridge. It can come together. Or you need a floating stage. So it becomes a way to constantly reconfigure the city in a dynamic way. So, and again, by the way, that's something that has been done for a long time. The city of Venice, once a year during the Festa del Redentore, puts together all the gondolas to create a temporary bridge. But I think that's the beauty of technology, that it's not about creating new needs. Many times, it's just going back to things we've always done or always wanted to do, but do them in a different or better way. Now, so we are designing the boats a bit like drones. We're putting for motors, for propellers. We tried this configuration. We tried with water jets. This is a first little scale model, 1:4. Here's been tested in the canals of Amsterdam. You see it's very easy to control. Like drones, drones are very easy because you mount them quickly. You got a board that controls each of the motors, and so easy to mount and control. You see it here again. It's symmetrical, so you can move one way and the other way. We told the mayor, even if the research fails, no worries, we'll open a toy company, because everybody seems to have so much fun playing with this on the canals in Amsterdam. So, and this also becomes like a big sensing platform for the city. So, as I said, these are self-driving, so they use the same three-dimensional scan of the city we saw before for the car, the LiDAR. So every second you got around 300,000 three-dimensional data points. And that becomes a way to scan the canals. We're using this to look at other things in the canals. For instance, differential movement of buildings and facades. It's very important as well in Amsterdam. So again, the data you collect can unveil new dimensions of the city. So here you see all these kind of points collected every second, how they create like a constantly changing three-dimensional model of the city. And in the last 2 minutes, I will share with you a couple of other things about stuff like this. And I know in Dubai, you're all super excited about this. And, some people think that this will be the future of urban transportation. Now, I think that is rubbish. And the reason it is rubbish is that, these are great. Drones are great. But, but we cannot scale up drones in cities. And the reason is very simple. Technology can change plenty of things. But technology cannot change physics. And physics means that if you take the weight of your body, of my body, and you just want to keep it up there, in midair, let alone move it, you need tons of energy. You generate a lot of noise, and you generate a lot of disturbance. That's just physics. You need to move air in order to keep something floating up there. And, just to give you an example, in New York, there's a few helipads. There's a few tens of flights every hour taking off from some of the helipads, and everybody in the neighborhood complains. But if you want to have a little impact on mobility in Manhattan, you don't need tens of flights an hour, you need tens of thousands. You saw the number of vehicles we have in Manhattan is in the hundreds of thousands. So, that will never be possible, I think, in dense cities. Drones could be interesting outside of cities, could be interesting where, there's not much infrastructure, very interesting projects in Africa. Drones can be interesting as well when you got small ones in order to sense the city, to monitor the environment, also to play with. That's a project we just completed in Italy for the first time in the world. We used drones for doing graffiti in a very precise way. That went viral a couple of months ago. I will not show you the video. But I want to finish with another project we've been doing with drones on the MIT campus. And drones, again, small drones, they can help us for other things. On the MIT campus, we have a problem. And the problem is that the campus was built by engineers. It's not very easy to navigate. There's plenty of buildings. They all look the same. Each of them has a number. I'm in building 9 to 50. Sometimes I send people to building 36, 136. That's computer science. A lot of people get lost in the middle. So we developed this project with drones in order to help them, and in particular, to rescue Harvard students. Sound?
Welcome to MIT. Where would you like to go? Follow me, please. The Computer Science and Artificial Intelligence Lab is the largest research lab at MIT. And one of
To
the
your
world's
right,
most important
the Media
centers of
Lab.
information technology
To your left,
research.
the Stata Center.
Follow me, please. Approaching your destination.
You have arrived. Welcome to Senseable City Lab.
Goodbye.
Thank you. One final image. So we started talking about the future. So we said the future is something we predict. The future is something we build. We need to experiment. But we need to experiment also in a way we don't make mistakes. So it's very important that we work together with cities to avoid this. This was actually a piece of future. It was about dockless bikes that generated issues in cities, pollution, bike pollution for the first time in this kind of bike cemetery. So it's very important that we actually try new technologies, work with citizens, with cities, with companies in order to experiment, trying to avoid mistakes, but trying to speed up and accelerate the transformation of the present. Thank you.